Today we're going to look at another application of the definite integral, and this is called volume of solids of revolution. And today we're going to look at a particular method called the disk method. So let's see how we could get that. All right, we have discussed how to get the area under a curve. And again, if we look at the diagram, I have the area bounded by a curve and the x and y axes. So here I have a line and bounded by the x and y axis. Here I have a horizontal line to a certain point here, bounded to the x-axis and the y-axis, a vertical line drawn to the x-axis and bounded by the y-axis, and here the half of a parabola and some horizontal line and the y-axis. So we have these areas, and what we're going to do is we're going to rotate these regions about the x or y axis. And this circular arrow here tells us this is called the axis of revolution. So in the first diagram, the axis of revolution is the y-axis. In the second diagram, it's the x-axis, and in the third diagram, it's the y-axis. All right, so what will happen when we take this area, cut it out, and rotate it around the axes as indicated? Well, the first thing that will happen is that we'll take this out, rotate it around, and it would be reflected on the other side. But there will be a circular base here because this edge will outline a circle, and then we would rotate it back. And what we would get is a cone. And this cone is solid. It's a solid cone. In the second one, we have a rectangle. We flip it down around the x-axis. But again, as we rotate it around out of the paper, around back to the paper, we will form a circular base coming out. In the same way here. And then when we rotate it back behind the paper, we'll get this. So we get what's called a cylinder. And this is a cylinder that is filled in because we're rotating the area. And then finally, when we rotate half of this parabola out toward us and around, it will be reflected here. And it would form a circular base coming out and then back in. And this is called a paraboloid. So these, again, all of these are solids. They are solids. We are rotating the area. Notice that the area, one of the boundaries is the x or y axis. It's the area under one function to the x or y axis, and we're rotating that around the x or y axis. So let's look at a few more pictures. So the first picture here is like our do now problem 1b. And here the axes aren't labeled, but this is x and y. And we're rotating around the y-axis here. And we get this solid of revolution. And then this one is like our 1a, where we rotate the triangle. But this triangle, though, is bounded by the x-axis. So technically, we're rotating this about the x-axis as well. Whereas in 1a, we rotate it around the y-axis, and we still get a cone, as we see in this picture. And then finally, this picture is any function. Notice this piece. We shaded the area under the function to the x-axis, bounded from x equals a to x equals b. And when we revolve this region about the x-axis, we get this shape. And remember, with solids of revolution, we always have like a circular bottom or base. And it looks almost like a vase. But notice that this rectangle this generic rectangle that we use to get the area in the region rotates to get what's called a disk. So that rather than summing areas of infinitely many rectangles, we are going to rotate all those rectangles and sum infinitely many volumes of these disks. So let's look at the next page and summarize. So first we'll define a solid of revolution. A solid of revolution is formed by rotating the area of a region about a vertical or horizontal line, and this vertical or horizontal line is called the axis of revolution. Now, the most popular vertical line or horizontal lines are the x and y axes. So for a vertical axis of revolution, we use the y-axis, and its equation is x equals 0. For a horizontal line as the axis of revolution, we may use the x-axis, and its equation is y equals 0. The axis of revolution do not have to be the x and y axis. They could be equations of other lines, but for now we'll be focusing in on the axes of revolutions that involve first the x-axis, then the y-axis, and later in another lesson we'll consider others. So let's go back to this diagram. Okay, so here we have a function y equals f of x graphed from x equals a to x equals b. And if we were to find the area bounded by the function to the x-axis and the lines x equals a to x equals b, we see that a vertical rectangle would span the region. Okay, let's just try to get that vertical rectangle in here. The top of the rectangle would always hit f of x. The bottom of the rectangle will always hit the x-axis that has an equation of 0. So the area bounded by this region would be the definite integral from a to b of the top curve, f of x, minus the bottom, which is y equals 0. So really we don't even need to put it there with respect to x. So we would sum up infinitely many areas of vertical rectangles. Now, if we revolve this region about the x-axis, then let's see what happens. The vertical rectangle, all the rectangles that we used to find the area, are now going to be rotated, and we're going to sum up the volumes of those to approximate the volume of the solid of revolution. And if you notice, this rectangle, which was originally in pink, I'll put it in red. When it's rotated, it swings around out toward us and back behind us, and it forms what looks like a record, or what's called a disc. So let me just make a picture of it here. So here we're rotating around the x-axis, and our rectangle is sitting here. This is one of our representative rectangles that has a width of delta x, which morphs into that dx. And this is the height of the rectangle, which is the value of the function at that x coordinate. And what we're doing is we're rotating this rectangle around the x-axis. So I'm just going to put this in black. Okay, so this rectangle will swing around. First, I'm going to reflect it as a guide. Down. That's its reflection. But the top will swing around out toward us, and this edge would swing around out toward us. And then as we swing this rectangle back behind the paper, we have another circle which has like a very, very small edge. And this is all solid. This is called a disk. So to find the volume, the volume of the solid of revolution, we're going to sum up the volumes of these disks as we move from x equals a to x equals b. And what is the volume of such a? Well, let's see. Well, it's the area of the circle, the surface, times the width, because this disk has a very tiny width. And remember that the delta x will be approaching 0. So the area of a circle's pi r squared, and the width is delta x. But now the key is to represent the radius. The radius of our disk is this pink rectangle, or now I'm going to shade it in blue, but it's this original rectangle here. And the height of that rectangle is the radius of our disk. So we could represent f of x, but we square it, delta x. And as we sum up infinitely many of these from x equals a to x equals b, and we make the number of rectangles increase without bound, we finally get the following formula. When we revolve around the x-axis, the pi will go outside the integral because it's a constant. We're still summing up volumes of disks from x equals a to x equals b. That's why it's important to know area. But we have to square the radius, and the delta x becomes dx when we take the limit as the number of rectangles increase without bound. And remember, this is from x equals a to x equals b. And that would be the integral if we revolve the region about the x-axis using the disk method. But keep in mind that in order to get the disk, the rectangle has to be perpendicular to the axis of revolution. So I'm going to summarize on the next page. So I re-summarize this here. With the disk method, the rectangle must be perpendicular to the axis of revolution, or the rectangle has to have opposite orientation to the axis of revolution. So since the x-axis is horizontal, we must use a vertical rectangle to generate a disk. So just as we have in area, the theme is the same. When a vertical rectangle spans the region, and we rotate this region about the x-axis via the disk method, then the integral would have a pi on the outside. The limits of integration are the same as in area, but this time we square the function. We square the function with respect to x. Now, when would we use a horizontal rectangle? Let's see in this next diagram. So I have here a diagram where this piece of the parabola, and we saw this in the do now, this piece of the parabola, is rotated around the y-axis here. Okay, so we see that the rotation is around the y-axis here. And there's an imaginary line going this way. And we end up having a paraboloid, as we see below. So the area of this region, bounded by the parabola and this horizontal line, whatever its equation might be, and notice one of the horizontal lines that bound this region for area is the x-axis, which has an equation of y equals 0. When we write. So, yeah, okay. Now, how do we do that? Well, let's make a diagram again. So I retraced the region that we're rotating. So we're rotating the area of this region, okay, to get this paraboloid about the y-axis. Okay, so here to get a disk, well, first of all, let's review how to get area. If we were to get the area of this region, we would find that the most efficient rectangle would be the horizontal rectangle. And notice that the right side will always hit f of x and the left side will always hit the y-axis, which has an equation of x equals 0. All right, so as an area problem, this would be set up as the definite integral from y equals 0 to y equals b, because this is the line, I labeled it y equals b. But now we have to solve for x. Now this problem summarizes everything we've done so far. So I'm going to start with a very simple region. This region is bounded by the line y equals negative 2x plus 4, the x and y axis. So let's try sketching it. And again, we cannot do any of these problems unless we have a sketch of the area of the region. So when we sketch this line, we see that its x-intercept is 2 and its y-intercept is 4, and it has a negative slope, and we connect that. So the region bounded by the line, the x and y axis, is simply this triangle here. And now we don't need calculus to find the area of the triangle, but I just like to do this emphasizing the technique using calculus. So we're starting with an easy question. All right, now if we were to find the area of this region R using, in terms of x, we must use a vertical rectangle. So we draw a vertical rectangle here. We integrate with respect to x. So the integral would be from x equals, now this is x equals 0, this vertical line, to x equals 2. Of the top curve, in terms of x, is negative 2x plus 4, minus the bottom, which is y equals 0, which we don't really need to put, and you get this. So that integral represents the area in terms of x. Now, if we want to set up an integral in terms of y, then we must use a horizontal rectangle. Okay, because the width of this rectangle, the delta y, is here. Okay, so here we have to do everything in terms of y, and that integral would be from y equals 0, which is the equation of the x-axis, to y equals 4, which is the equation of this horizontal line. Okay, and it is right minus left. But remember, we have to solve for x. So let's do a little bit of math here. We have y equals negative 2x plus 4. We have y minus 4 divided by negative 2 equals x. So that the horizontal distance in terms of y is y minus 4 over negative 2. That's our function in terms of y, minus x equals 0, which is the y-axis, dy. So that's a good practice. Remember, area is top minus bottom for vertical rectangles, right minus left for horizontal rectangles. All right, and these will help us answer the next two questions. Now, if we rotate this region, this triangle, about the x-axis, so let's make a little picture for about the x and y-axis. So if we rotate this triangle about the x-axis, well, it'll be reflected down this way, and we'll have a circular base. If we rotate this triangle about the y-axis, then it will be reflected down this way and have a circular base this way. These are two cones, but these cones do not have the same volume. They're two different solids. Okay, so let's see. So when we rotate around the x-axis, again, to get a disk, the rectangle has to be perpendicular to the axis of revolution. So this would use a vertical rectangle. This would use a horizontal rectangle. And in the same way, these integrals, you could start setting up. Pi always goes on the outside. The limits of integration in terms of x are the same as area. This is the integral from 0 to 2. In terms of y, it would be the integral from 0 to 4, because those are the two horizontal lines that still bound the triangle, so they do not change. The only difference is that about the x-axis, we do this in terms of x. About the y-axis, we have it in terms of y. So the radius of this disk, this is the height of that red rectangle, and that's just the function negative 2x plus 4 minus 0 squared. And in the same way, if we revolve around the y-axis, the height of this horizontal rectangle, which is the radius of any such disk, so let me just draw the disk in here, would be this horizontal distance, which is what we found when we solved for x. So this would be y, oh, wrong color, y minus 4 divided by negative 2 squared dy. And that's it. So basically, with the disk method, this is what we have to remember. All right, let's take a look at a more complicated one. All right, this one I'd like to work out with you. Region R is bounded by y equals the square root of x equals 0, y equals 0, and x equals 4. Find the volume of the solid of revolution. All right, so again, first sketch. Okay, so y equals the square root of x is our square root function. X equals 4 is some vertical line to the right, A y equals 0 and x equals 0 is just the x and y axis. So the region we're talking about is this. So if I asked you to find the area of this region, again, we always try vertical rectangles because they seem to be easier. And the top and bottom always span the same two functions, the top and the bottom. So the formula for area would be from x equals 0 to x equals 4 of the top curve, y equals square root of x, minus the bottom, y equals 0 dx. Now, I didn't tell you to find the volume of the solid of revolution when we rotate around the x-axis. Okay, so keeping that vertical rectangle. If we rotate that vertical rectangle, we will get our discs again. And don't be afraid to draw a little disc there so you could see it. And the radius of the disc is the height of the rectangle. So our integral would be pi on the outside, same limits of integration, 0 to 4, but this time it's the square root of x, minus 0 squared, and dx. So let's integrate that. Pi equals the integral from 0 to 4 of x dx. This is easy enough. The antiderivative is x squared over 2 by the power rule. And I always factor out the pi. I don't put that in there. I multiply the answer by pi at the end. So I get pi times 4 squared over 2 minus 0 squared over 2. And the answer would come out to be, I believe, 8 pi. And that would be the volume of the solid of revolution. Okay, let's see this demonstrated on some software.
I wanted to show you an animation of the problem that we've just talked about. So I have a function that is y equals the square root of x over here. And the axis of revolution is y equals 0, which is the x-axis. And notice I arbitrarily picked the interval from 0 to some right endpoint b. But right now, I just wanted you to see what doing with the rectangle. So here I have 5 rectangles. So I could use 5 rectangles to approximate the area under this curve, a vertical rectangle. And so if I put all 5, I have this, and the sum of the areas of these 5 rectangles would approximate the area under the curve. All right, I'm just gonna hide these rectangles again. Now, let's rotate this area about the x-axis. We're gonna reflect it first. Okay, now with that rotation, the rectangles are being rotated as well. They're coming out first and going behind. So let's see what the disc would look like. And that is our disc. Now, delta x is overemphasized, but that's our disc. And if we see the 5 discs here, the volumes of these 5 discs would approximate the volume of this paraboloid. Now, if we increase the number of rectangles to, say, 10 of them, okay. Notice that we have 10 discs, and the error, these little edges that are protruding, are becoming smaller and smaller and almost filling up the paraboloid. So as we increase the number of rectangles to, say, 50, and we see them, notice that we hardly could see the edges out here, and the discs are really narrower. So as the number of rectangles increase without bound, the delta x gets smaller and smaller, and these little edges here, which are really the delta x's, they are becoming negligible. So as the number of rectangles increase without bound, our area, our volume of the solid of the revolution is coming closer and closer to the
So let's
actual
take a look at
answer.
this last problem. We have a region that's bounded by a parabola y equals x squared, the vertical line x equals 2, and the x-axis. And we're going to revolve this region about the x-axis. And the same parabola y equals x squared, the line y equals 4, and the y-axis. And we want to find the volume when we rotate this area about the y-axis. So let's sketch the regions in 2 dimensions to see what the areas look like. So if we take a look at the regions, x equals 2, y equals x squared, and the x-axis bound this region. And y equals x squared, y equals 4, which is at the intersection point, the same point up here. And the y-axis is this region. Now, to generate a disk revolving around the x-axis, remember, the disk has to be opposite orientation, so that if the x-axis is horizontal, our disk is vertical here. Here, if the axis of revolution is vertical, our disk is horizontal. And these would be the same rectangles we would use to find area. Okay, so again, remember that when we have a vertical rectangle, whether it's area or disk, we integrate with respect to x. Here, horizontal rectangle, we integrate with respect to y. This is the key. So now, outside each of these integrals, we put a pi. And by the way, I should draw in my disks here. So that's my vertical disk. Here's my horizontal disk. Okay, so the x limits of integration would be from x equals 0 to x equals 2. And the radius of the disk is the height of the rectangle, and that's at just y equals x squared. But we square that. Because remember, the area of a circle is pi r squared times delta x, or dx. In this problem, though, we have to integrate with respect to y. So the y limits of integration are from y equals 0 to y equals 4. Now the vertical lines become horizontal. But now we have to solve this equation for x to express the horizontal distance in terms of y. And that becomes the square root of y, positive or negative. But when we square it, we get, it doesn't matter, we just get y dy. All right, now these are not the same solid. We'll have different answers, but let's calculate the volumes by using the first fundamental theorem. Pause the video and try it. Okay, so for the volume of the solid, when the regions rotate around the x-axis, we integrate x to the 4th, which is x to the 5th over 5. We leave the pi on the outside. We use our first fundamental theorem, and the answer is 32 pi over 5. I hope I did that correctly. And then here, when we square the square root of y, we get y. The antiderivative is y squared over 2. We substitute 4 and 0 for the first fundamental theorem, and the answer is 8 pi. Let's take a look at a GeoGebra animation of this problem.
So here's another application. I'm using GeoGebra, where we rotate the region bounded by y equals x squared from x equals 0 to x equals 2 about the x-axis. So here is our integral right here. The left bound is 0, right bound is 2. But I just wanted to show you what that solid looks like here. When we rotate that area about the x-axis, it looks like a funnel, actually. It's a funnel. And yeah, so I thought that was interesting. And here's its approximation, 20.11. Now, if we rotate the same region about the y-axis, well, the limits of integration, we use a horizontal rectangle from y equals 0 to y equals 4, as we have here. And let's see what that solid looks like. And remember, this is a solid. Even though it looks like it's a surface, it's filled in because we are rotating the area. And that looks almost like a paraboloid. Okay, so I just wanted to show you the pictures and the visualization.
Please note that the answers that were obtained here, I should say here and here, use the approximation for pi to get that decimal answer, but they are equivalent to the answers that we got beforehand. Okay, so that takes care of volumes of solids of revolution using the disk method. Have a wonderful day.